Hi, my name is Zane Carter, and this is my physics final project over the physics behind billiards. In the first scenario, Newton's third law of motion is presented. The third law of motion states that for every action, there's an equal and opposite reaction. Since m2 starts at rest, its velocity will be equivalent to 0. m1 will gain a velocity of v1 cb. This causes m1 to act in the positive x direction. After the contact point is made between m1 and m2, it is assumed that m2 will have a velocity in its own positive direction because Newton's third law states that for every action, there is an opposite and equal reaction. The opposite reaction of this experiment will be the force of m2 acting on m1 after contact is made. After the contact is made, the force of m2 acting on m1 will cause m1 to have a velocity in its own negative direction. This further proves that Newton's third law of motion, where for every action there's an equal and opposite reaction, is true. After the collision has happened and each ball is moving in each direction, Newton's third law states that every action has an equal and opposite reaction, which is proven in the first scenario of my experiment. Because m1's initial velocity is in its own positive x direction, after the collision, the force caused by the object ball causes the cue ball to have a velocity in its own negative direction. Here you can see the initial contact of m1, the cue ball, with m2, the object ball. Initially, m1 had a velocity. Here you can see after m1 has made contact with m2 and has bounced off of m2, m2 has a velocity and m1 starts to roll backwards, giving proof to Newton's third law of motion that every action will have an equal and opposite reaction. Newton's second law. Newton's second law states that an object's rate of change in momentum is equivalent to that of the force acting upon it. This can be shown in the equation force equals mass times acceleration. You assume that the masses are equal, and it leaves you with force equals acceleration. Here in the diagram, you can see that the cue ball has an initial velocity of v1 cb toward m2, glancing the side of it. Here you can see the center masses for the object ball and the cue ball being drawn to give them their own respected x-axis. Here you can see being drawn the y-axis between the object ball and the cue ball. The y-axis is being drawn on the contact point between the two. This contact point causes the object ball to gain acceleration due to the force being given by the cue ball onto the object ball. After the cue ball makes contact with the object ball, the cue ball's velocity now has another direction that is not similar to the one it had before it came into contact with the object ball. As briefly mentioned before, the direction of object ball's velocity will be along the x-axis created by the center masses of the two objects in the collision. Here you can see being drawn the direction of the cue ball's velocity after the contact, which is written as v2 cb, however going in another direction opposite to what it was going initially. The direction of the cb's velocity is going along the y-axis drawn at the contact point between the object ball and the cue ball. Here you can see depicted Newton's first law of motion, which is force equals mass times acceleration. However, like the other equations used before, the masses are assumed equal and cancel out, leaving it to be just force equals acceleration. This means that they are directionally proportional. Directionally proportional means that when one increases, that means that the other increases. You could also view it as one acts onto another, it increases the other, such as when a force acts on another object, it increases its acceleration. And as the acceleration increases, you can assume that the force acting on it has also increased. In the following experiment, this prediction is proven and shown. You can see that the initial velocity of the cue ball hitting the object ball that is at rest causes it to move in its own positive x direction. Here you can see that m1 has an initial velocity and makes contact with m2, causing m2 to have in its own positive x direction, leaving m1 going in its own positive y direction. In the third scenario, you can see all three of Newton's laws of motion, including elastic collisions. Elastic collisions is the concept of the conservation of kinetic energy and the conservation of momentum. The conservation of kinetic energy's equation is shown below, and that is 1/2 m1v1 squared is equal to negative 1/2 m1v2 final squared plus 1/2 m2v2 final squared. And since you assume the masses are equal, in the equation simplifies to being the initial velocity of the cue ball squared before the collision, which is before the collision, is equal to negative v2 cb final squared, which is the velocity of the cue ball after impact, plus v2 obf squared, which is the velocity of the object ball after the cue ball has hit. The equations for momentum are shown below. Momentum in the x direction and momentum in the y direction. Momentum in the x direction is shown as m1 v1 of the cue ball, which is the forces of the cue ball, are equal to m1 v2 cb, which is the forces acting on the cue ball after impact, plus m2 v2 ob, which is the forces acting on the object ball. However, you see that there are no 1/2 m2 v1 values or m1 or m2 v1 values. That's because the initial velocity of the object ball is at 0, so it's at rest, so it just cancels out for all the equations. Masses do cancel out. Again, it simplifies down to the initial velocity of the cue ball is equal to the velocity of the cue ball in the x direction only, plus the velocity of the object ball in the x direction only. And that's their own respective x directions. Initially, there is no y direction of either because object ball is not moving at all, and the cue ball is moving in one direction, so we give it the x direction. Again, the masses cancel out, so the equation ends up being 0 equals velocity of the object ball in the y direction only minus the velocity of the cue ball in the y direction only. You could actually find that when the two objects collide in a system and bounce off at each other at their own respective angles of the horizontal axis made between the two center masses, that angle actually adds up to 90 degrees, and I will show that in the following diagrams. As you can see, the cue ball has an initial velocity going toward m2, the object ball, at an angle. M2 has a velocity going in the x direction of both m1 and m2 created by their center masses. M2, as you can see, has a x component and a y component. The x component of m2's velocity is called v2 FOBX, which could also be written as v2 OB F cosine of theta. Theta representing the angle made by the two axes made by m2, one being the axis going across the center masses and the other being the axis of its own x-axis. The y component of m2's velocity is called v2 FOBY, which is equal to v2 FOB sine of theta. As you can see here, the y-axis is drawn between the two masses at the contact point. The contact point also determines where m1's velocity is going to be going. It does this by the fact that m1's direction of velocity is parallel to that of the y-axis, or the line made by the contact point between m1 and m2 when m1 collides with m2, going at an initial velocity equal to that of m1 v1 initial, or v1 cb initial. As you can see being drawn, the y component of m1's velocity is equal to that of v1 f sine theta. The x component of m1's velocity after the collision is equal to that of v1 f cosine theta. Theta again equaling the axes made by m1's velocity after the collision, being the x-axis respective to m1 itself, and the y-axis made by m1 and m2's collision. The next equation we can look at to prove that Newton's 3 laws of motion and elastic collisions all apply to these cases is the fact that both angles made by m1 and m2 add up to 90 degrees after an elastic collision occurs between the two. M1 has an initial velocity and makes contact with M2. This contact is what makes the 90-degree angle possible between the two objects. The contact of M1, the cue ball, hits M2, the object ball. The directions of their velocities make the 90-degree angle possible. Using Newton's 3 laws of motion and the concept of elastic collisions, considering the conservation of kinetic energy and momentum in a system of two objects. I hope you enjoyed my project today, and I hope that the scenarios that I presented